So, hi everybody, and welcome to the lecture today. Today we will have another great lecture on high networks. The topic specifically today is about switches, both legacy switches as well as SDN switches. And as you see here, we have a long list of topics to discuss. So we will first start with a discussion of what we have inside the switch. Here we will see diagrams of switches. Some of them will be familiar to you because we have seen them also in introductory classes on computer networks. Some of them will be new to you. And this will guide us today, these diagrams, as the focus will be to dive inside the switch and try to get a better understanding of what is there. Secondly, we will focus a little bit more and we will discuss together the input processing of a switch, and we will do this using the peer instruction process that by now I think you should all be familiar with. So here we will have our PI focusing on input processing. Okay, then the third topic we have for today is to see what type of memories we use in switches. Next, we will discuss and we will see a new. We will discuss about new generation switches that are currently built and that relate to software-defined networking. And here we will focus and we will use as a motivating example and as a topic for discussion a new switch that's called 6-pack, and that is that was introduced on March 2015 by Facebook. By Facebook. So not the most common type of player we would expect to build switches. But indeed, Facebook has started building its own switches. And we will see what is special about them, and so on. Okay, topic, going further down this fantastic list, topic number 5, we have ASICs. Who knows what is an ASIC? Fantastic. Well, not that fantastic. It's just a single person, but it's okay. Okay, so ASICs stands for Application-Specific Integrated Circuits. It's all about hardware, and it's basically chips. And we will discuss them in the context of switches a little bit to understand better the hardware of switches. Okay, and finally, basically, you will realize that almost up to this point, we will be discussing about hardware today, although it's not my core topic. But I think it's very interesting and important, and also an opportunity to understand these elements better, the switches. We will close the lecture talking about a protocol that is called diffconfig, that is the sibling of OpenFlow. And this is on the software side of our suites, so that we have a broader understanding both of the hardware as well as of the software inside the suites. Okay, as always, please ask me questions, interrupt, participate. I'm erasing this, okay? Okay, let's start with the diagrams. Diagram number 1, it's pretty simple. We will learn two things here. So this is a view of what is a switch, okay? So in one view of a switch, we have on the bottom what is called the fast path. Okay, and on the top we have a detour towards what is called the slow path. The slow path. As you can imagine, here we have packets coming in, and the packet can travel along the fast path. That's the good scenario. But a packet may also have to travel along the slow path. That's the bad scenario. So, the fast path is entirely implemented on hardware. And this is in particular a chip. It's a chip that is implemented on an ASIC, as I said before. So here it goes through the various stages, and at the end is forwarded from an input port to an output port. If things go well, it will be handled entirely on hardware, it will be processed very fast, and it will be forwarded to further on. Here we have also a table, as we know, in a special memory that is called CAM or TCAM. We will discuss this further down. Okay, if we don't find an entry here in the table, then the packet is sent to the slow path, and the slow path involves the CPU as well as software. So this is now works on software, therefore it takes much more time to be processed. And here we have memory again, but this is usually SRAM. Okay, so this is diagram number 1. Okay, and here we keep from here that in a switch we have the fast path and the slow path. The fast path is entirely in hardware, and the slow path, it involves software, the central processing unit, and slow memory. Where here we have much faster memory, and we have everything in hardware. Fortunately, when packets go through a switch, usually they are handled in hardware. And most of the packets are handled in hardware, and if we have few entries here that basically indicate how to forward a switch, if these entries are for the so-called elephants, elephants are the large flows that have many packets, like the flows, for example, of a video stream online, which will be, millions of packets, and therefore these can, if we have the elephants here, then most of the packets will be processed very fast. However, if we don't have a match here, we might go to a second table that is in software, and there the lookup operation, because it happens in software, is much more slow, and therefore it is usually preferred to put the elephants in hardware and the so-called mice, the small flows, in software. Yes?
RAM memory, where the elephant should go, can be changed. It's implemented in hardware, but it's static. It can be static because it needs to change, depends on what we set in the network.
Yes, it can be changed.
So if an elephant is in SRAM, we can bring it to the CAM.
Right.
So balance the network if something is not how it's supposed to be. There's a lot of packets to the CPU. We can bring down the elephant to the CAM.
Right. So the ideal scenario here is to have the elephants on hardware and to have the mice on software. What is bigger, TCAM or SRAM? That's it. A second before I erase it.
Isn't CPU included in hardware?
Yes, but CPU is controlled by software.
Control, yes.
This is only hardware.
And it's static. We can change the flow of things in the hardware thing.
No, we can change the hardware. It's not static. We can write entries in this memory.
Now, since there is no software, Then we use
The software, correct, the software that controls this can insert entries. But the packet processing that comes in, comes out, happens in hardware.
Okay. So, even if the TCAM is fast enough, if bringing things from SRAM to TCAM is slow, so we can εξεργαστούμε process data too fast if the software isn't fast enough. So even though we have the speed in the hardware part, again we need the software to be fast enough. So why have two different memories?
Sava, if I understand correct your question, let me see how to answer this.
Everything is defined by software, and we have two different kind of memories. Why have two different kind of memories? And it's useless. I see it's useless.
No, it's not. What is important to understand here is that this path, the fast path, it's much faster than the slow path. Okay, even if this is controlled by software, because the packet that is processed, the processing happens entirely in hardware.
So there is nothing to do with software over there.
No,
Okay,
in the fast path there is no software involved.
Should I add something?
Yes, Lester,
that
please.
maybe help-
Please.
help? When we're talking about hardware and ASICs, we're talking about low-level software. It's not high-level software, like writing in Java, for example. It's low-level. So the whole process is a lot faster than when you're dealing with a high-level language, like when you go up the level as Fortas describes.
Okay.
So that's the main difference. We're talking about firmware, actually. If you've ever heard
Okay, yes, I got you.
Now you understand.
Packets always go to the TCAM, and when there is no entry or no, it goes then to the
Yes,
slow path.
yes.
You always prefer the fast path.
Yes,
And then
yes. Other questions?
So, what is elephant and mice? How
What?
do you differentiate elephant and mice? Elephant and mice in G, we have. Do you differentiate how the switch differentiates that?
Okay, good question. So it's basically the controller that does that. So in OpenFlow, it's the job of the OpenFlow controller to do this. Okay, so let's move now to diagram number 2. Okay, this diagram you know it, but we will see it again. Okay, so here we have a different view of a switch. In this view, we first see on the left the input ports and the input processing. This is the stage that a packet goes through when it arrives to a switch. Within the input processing, it goes through different stages. In computer networking, last semester, what we taught was basically that we have three stages here. Stage 1, stage 2, and stage 3. In these stages, at the very first stage, it concerns the physical layer. Then the second stage concerns layer 2. So switching and MAC, the MAC protocols. And the third stage concerns layer 3.
Routing and IP.
Routing, the fib table lookup, and so on. Okay. So this, of course, I'm not going to draw it. It's repeated in every input processing unit. Okay. Can anyone of you think what functions, tell me what functions we have here in layer 2 processing and layer 3 processing?
The layer 2 we have to find out the MAC address, so we would need an ARP function. I'm not sure, I'm just guessing.
No, Sava, that's not correct. Let me say here, actually the first part we do need to learn to find out the MAC address, but ARP is not involved here. So here, this diagram, it concerns only the hardware. Okay. The diagram we see here is the fast path, essentially. Okay. Let me write this here. Okay. So here we have the physical part, so the demodulation of the signal, the digitalization of the signals. Here we have an analog signal. Here it becomes digital. We have bits on the right side. Here we have the layer 2 functions, and here we have the layer 3 functions. Now I'm not going to tell you much more here for a moment, but because I have prepared a PI question to see this in more detail. So we'll discuss this in a bit together. But for now, just remember what we learned from computer networking course, that we have these three stages here. Yes?
Yes, actually, if I remember right, the level 2, they actually give us a MAC layer access that we can MAC addresses from the packet. And layer 3 actually give us an IP level that we can learn IP and the port number of source.
Correct. Alexander, right? Also, what else do you remember? What other important function happens here in the input? Yes. Encapsulate me. True. Yes, true. It's mostly correct. But other major function. What major function happens here?
I don't remember a function. I think there is a problem. The head of line blocking.
Right, you remember right. There is the head of line blocking, but let's forget about it for today. Okay, let me ask this in a different way. So who can figure out where is the forwarding table in this diagram?
Between the switching fabric.
Come on, draw it.
I don't want to.
Other try? Who agrees? Or is there another opinion before agreeing disagreeing? Yes? Yes.
I think too, it's in the
Switching fabric.
Not really sure about that, but I think the switching fabric is the hardware, basically the lines that just send the packets to where they should go, so nothing has.
I have the table.
I think you are right. True. So other opinions?
Maybe in output processing.
Output processing. Okay, output. Who says output processing?
And something.
Yes.
The switching table in fast path is implemented in hardware. Hardware, it's not cheap, it's not software, so it's not clever enough to use a switching table in every input processing because it's expensive. Also, if every hardware table needs the same inputs, we can use only one. So it's much clever to use it in switching fabric than to use three hardware tables in every input processing.
What's your name?
Michalis.
Michalis, interesting argumentation, but it's not like that. And it's actually, yeah, it's. Alex?
Actually, I think so. Switch can check the hash sum, the packet, when it's encapsulated, to check if the packet is right and it's going to be transmitted or it's going to be dropped.
Okay. And where this will take place?
Layer 3.
Or even layer 2 if we have.
If the switch is smart enough, yeah.
No. So it will. This happens here, and maybe here too. Excellent. Okay, but back to my previous question: who has a different opinion? I haven't heard yet the correct answer. Yes, Mr. Reed.
I'm not familiar with this topic. It's just that my logic says that the table must be before the switching fabric in the input processing, because when it enters the switching fabric, it must know where to go. That's the logic.
And that's correct. So precisely. So, as Lefteri said, like if you think about it, the table, the lookup has to be before the switching fabric, because when we enter the switching fabric, we have to know in which output we go. Okay, the switching fabric is a bunch of wires, but it's the most expensive part of the switch. But you know, these wires might switch at 700 gigabits. Because if we have, you know, 40 gigabit ports here, and we have 16 40 gigabit ports, this must support the aggregate.
How many switching tables there are? There are one
Great.
or three?
So a big lie that we learn is that there is one table, forwarding table. But that's not true. Here, in every input port, we have one hardware forwarding table. Okay?
Tables are synchronous. I mean, every table has the same entries.
Yeah, it should.
So we use something that's expensive, multiple times, and we could use only one to do the same exact job.
True, Mihaly, but then this would be the bottleneck.
They like a RAM, DDR RAM, which have double wires, so it could access 2, 3, whatever we want to do, inputs at the same time. So 2 or 3 or 4 lines would access the same table at the same
Not a hardware guy, but I don't think that such a RAM could support this speed, 700 gigabits. And here we might have, you know, 20 ports, 40 ports could
So
be.
what's the answer to your question?
So that the table is here, it's in the input
level
processing. Yeah, it's at the level 3 of the input processing. And we have, it sounds counterintuitive, but we have a separate copy of the table here, here, and here, and in every input processing. So little lies when we learn about computer networks without knowing the hardware.
Thinking about adding something, because it took me many years to understand, and you know, since I understood it, I think it's interesting to mention. As Foda said in the first lesson, the difference of SDN is that it has open software and open hardware. And what does it mean actually? It means that most of the hardware that exists through companies is not available to public. So we don't know exactly how it's made. Only the guys in the company, let's say Cisco, know how exactly the hardware is implemented. So it's not open. There are some cases where hardware was opened by making available the designs and everything. And one such case is MIPS CPUs that were used in switches 10 or 20 years ago. And by making this available, we were able to study the design and make software that emulates this hardware so that we have the dynamics controller, and after all, we have software switches. But we did that because we knew exactly how the hardware was built. So this whole story about hardware, how fast it is and how it works exactly, especially in the latest and greatest hardware, we don't know exactly how it's made because it's corporate knowledge, and it's very, very expensive to get that. I mean, it's, you know, like top secret stuff. That's what I wanted to do.
So the switches that support OpenFlow are based on the MIPS architecture?
No. I just said the one example. So switches in SDN, but Xenofontas is more capable than me to explain that, are simple hardware switches. No open hardware. I mean, based on open hardware, nothing very fancy. very, very cheap also. But through that, through the MIPS and other stuff, we were able to create a new paradigm which is called network function virtualization. Like you have virtual software and you have virtual servers in data centers, you also have virtual routers, virtual switches, and that's in part goes together with SDN. It's a similar logic, and it's very, very, compatible with SDN also.
Okay, thanks, Lefteri. Okay, so now who can tell me what is in the output to close this diagram?
Probably it's the same, but in reverse. I would say that it goes layer 3, layer 2, layer 1, so it will end up to the target terminal.
Correct. That's correct, right? Is there another important function that we are omitting?
MAC address of the package.
Yes, but not this is in the output.
Yes.
Yeah, but not this one. Maybe I can help. Let me ask, where is queuing happening? Input processing.
Both ends.
Both ends? Who agrees? Both ends. Input? Output only? Yes.
I think that if the input process is too fast and the output process is too slow, then the queue will be in the input process. If the output process gets data faster than input can send them, then the queue occurs in output process.
Okay, let me tell you the answer to move on. So we have a queue both here in the output and here in the input. Okay, now the important queue, when we model routers as a single queue and we say we have packet drops, the important queue is the output queue. Okay, congestion happens at the output queue and not usually at the input queue. Okay, because here this switch is optimized to handle this traffic. This is 40 gigabits, so this is 40 gigabits, and this is 700 gigabits. But if we have all these switches sending traffic here, this one and this one sending traffic there, which is beyond our control, here we will have the queuing. So here packets will build up, and here packets will get dropped at the end. Okay. And here also we have the 3 levels. We have layer 3, layer 2, and the physical layer at the output. Okay, so this is a first level deeper on the hardware architecture of a switch. Okay, now we already learned something more. A switch basically has these components, and of course a router. Here, I don't want to repeat this, but throughout this lecture, switch and router are going to be the same. Since we are talking about layer 3 processing here. Okay, now I'm going to give you a question. We will go a level deeper, even deeper than this stage, And this question is about input processing. Okay, please distribute the question one every 3 people. Okay. Can I get one? Can I have one? Is there anyone? So in the back, you see what a level of, at a finer level of granularity, what the input processing looks like. Okay, and here the question is, I'm asking you to put the names behind the steps, and I'm giving you different possible answers in the back. What?
What is ACL?
Okay, ACL stands for Access Control Lists, and it is usually to implement used to implement firewalls and security policies.
The parser refers to the process of encapsulating the packet.
Yes.
The plan is to see if it's gonna send it the virtual LAN on the
What is the password again? What is the password of the should be.
Let me ask something. Switch and router is the same from now on. But is the router equal to a switch or the switch equal to?
A equals B, B equals A. That's the difference.
Switch is for layer 2 and
These switches are also for layer 3.
so switch is for layer 3 as well.
Yes.
You can see
So switch is a router.
because after
What's going on?
Okay, you can.
okay, probably we will have to which is done it is. And if you have to control this, if you have to.
A parser is the process of extracting the fields from the bits.
one is also kind of me. First,
Because access control.
yes,
And
because
two level 3
yeah. So I don't know. In terms of efficiency, this is more efficient
They are
because
all parser. Parser is the process of encapsulation of the packet or the
I
processing
don't know
of
what the heck it is.
It's the, what's your name? Leonida. It's basically, it's the process of turning bits into fields, saying that these 32 bits are an IP address. Okay, who says A? Who says B? C? D? Okay, we have C and D are fairly popular. Okay, let's see the answer today together. Okay, step one. Step one is the parser. Okay, the very first step is taking bits and extracting the fields from these bits. Okay, step 2 and 3 are layer 2 related steps. The first step, if you think it logically, to do the MAC operations, we have to first see in which VLAN the packet belongs. Okay, and then for this VLAN we do the layer 2 processing. So step 2 is the VLAN processing.
To me, it's easier because the switch checks if that source packet is allowed on that port or not. If it's not, then it doesn't need to look for VLAN.
You said that
ACL comes before VLAN.
You don't see the
Sam,
packet.
that's step 5.
That's
Yes.
to me, if that source packet is not allowed, then
I
it
will
doesn't
tell
need
you
to.
why.
Don't see the headers of the package. We don't know if you have to drop it or not. It's like firewall.
It doesn't need to.
One reason that it might be at the end is that you might also want to know in which output port you will send it. And you could have ACLs that match on the output port, that drop everything that goes on this output.
If we have ACL for source port, then
What?
if we have ACL for source port,
It can
source
still take place here. Still take place here.
is still fine.
Yes. But at step 5, you don't know yet. Before step 5, at step 4, you learn the output port. At step 2, you don't know yet the output port.
But I mean, ACL can be for source packet also. Any packets coming for this port we want to drop. We don't need to look for destination. We want to drop all the packets.
Yes. But then we would have to implement it both here and there. That's why they have it at the end.
I say something.
Yes.
If you remember from networks, the 325 course, when a packet goes from one computer to another, if we take the OSI model, the 7 layers, when it's in the wire, it's in layer 1, and when it goes to the other computer, it starts from layer 1, it goes up until it reaches layer 7, right? So if you think it this way, the solution is obviously C, because parser is what Xenofontas explained, and then we have VLAN and layer 2, which are both layer 2 issues, so it goes up, and then it's layer 3, and then it's ACL. And why ACL is a layer 4 issue, it is not something else? Because ACLs also contain port numbers, which is a TCP layer 4 concept. That's why it goes up in the layers, and that's why this is the right solution to the problem. That's the way to think about it, I guess.
True, that's also another point. This is logically, it starts from layer 2. Even before layer 2, when we look at which VLAN we are, often we have a header that is a VLAN header that is put on top of the MAC of the layer 2 header. So we start from VLAN, layer 2, layer 3, and ACLs that could also concern layer 4.
You explain those arrows after step 2 and step 3. What's the use?
Sava, let me first explain the arrows on the top, and we will discuss this if we have time further on. Okay, so now also keep in mind something other important. On top we have memories. Okay, this is everything in hardware what we see here. So the first two memories are called CAM, and the last memory is called TCAM. These are the CAM is of size 128K, and the second CAM is of size 16K. These memories are used for MAC addresses, for storing and looking up MAC addresses, the first one. The second is for storing and looking up IP addresses. This is for switching, this is for routing. And the last, the TCAM, is only 4,000 entries. And this is used for rules, complex rules that could have also wildcards. Like saying everything that is, let's say, 192 star, drop it. Okay, this is a wildcard. This is stored in a TCAM. Okay, do you want to wait 5 minutes more before the break to explain the CAM and TCAM? That's okay? Okay. Okay. Okay, let's assume that these are the memory bits, okay, the words. We have here 1000. and so on. And let's say that we want to search for a specific word. We want to search for the 0, 1, 1, 1. Okay, here we put in these memories, we enter what we want to search for. Okay, we enter, for example, 0, 1, 1, 1. In the context of computer networks, this could be the MAC address, or this could be the IP address, or the 16 bits of an IP address. Okay. Now, the nice thing about these memories, which are called content addressable memories, which means that we address them by their content. Okay, we give as input what is stored in the flip-flops. Okay, so here we will give as input the MAC address, and imagine here that we have, I don't know, 16,000 entries, and in one cycle, in one operation, this memory will give in the output if we have a match or a miss. Okay. What?
It can only be one match.
No, there can be multiple matches. Here actually it's not the correct. Let me put another string. So we have 1, 0, 0, 0, and then we have a match here and a match here. Yes, we could have in principle. But okay, let's keep it simple. Let's say that we have one match.
But that means that we can connect the same port, different ports,
Yeah.
the same computer, the same NIC.
In OpenFlow, if you remember, we have the priority. If we have multiple matches, then we keep the highest priority. Okay. But let's keep it simple. Let's say that we have one match. Okay, so we keep from here that this is content addressable, and in one operation we can look up 16,000 K entries. And here we take the output. Let's say that this is at position 1 here, or it could be a position 100. And we go to a second memory that says we go directly to position 100. That tells us the actions. The action that we take for this match. Okay. So this is called the content addressable memory. Now CAMs are very power hungry and very expensive. Okay. In contrast to SRAM. For this reason, when we have a CAM in a switch, it usually has a few entries. It has in the order of few thousand entries. But no more than that, because it increases a lot the cost of the hardware. So this is what we saw here, a binary CAM. We can have 0 or 1 in its position. There exists also the ternary cam or the T cam. In the T cam, we can also have a wildcard that basically says, I don't care about what is here, so we can do more flexible searches.
Still a binary, but we use wildcards.
In the implementation, to support the wildcard, actually we need 2 bits here. 2 bits for each position in the implementation, and this increases the cost. It's not a precise binary because you have 3 states. Okay. Okay, cams and T-cams are the memory that are used in the hardware of switches. Okay, the forwarding table is stored on cams and T-cams. Okay, we'll do a quick break. Okay, welcome back. In the first part of this lecture, we saw we got a deeper look into what the hardware of a switch looks like and of the different components in the switch. What we have seen so far, let me say that it applies both for all switches we know before software-defined networks, as well as for SDN switches. And the reason we are discussing this, it is important to understand the hardware of a switch when we are talking about software-defined networks. And one of the criticisms towards SDN is that when SDN came out, the specifics of the hardware were basically underestimated the characteristics of the hardware. And hardware introduces challenges in the operation of software-defined SDN switches, which I will discuss a little bit in the wrap-up of this lecture at the end. But now let's look at something different. Let's look at something new and exciting. We will see a new switch that has been designed by Facebook, and we will draw this to discuss also some topics that are generally interesting. And what has been done here, actually let me say Facebook is not the only one. Also Google has done similar stuff, and other players, major data center players are doing similar stuff. So we will watch now a short video about the 6-pack, and maybe we will see how we do it. We will take basically topics from the video to discuss them and explain them further here.
I'm Omar Baldonado, and I'm part of the Facebook network team. And I'll go over our vision today for the at-scale data center. When we started to think about this, we tried to redo everything with a focus on flexibility, scalability, and feature development speed. And so over the last year, we've announced different components of this new data center vision as they've gone into mass production and operational reality. First, we had to rethink the whole topology. We designed a new fabric topology that gave us the scalability and flexibility that our previous designs didn't have. Then we turned our attention to the switch hardware itself. There we started with the top-of-rack switch because it was the simplest place to insert new hardware and software into the network. When we designed Wedge, we wanted to be sure it would be more open and modular, and that it could be the basis for all future hardware and topologies. We also wanted to make the switch more like a server, so we actually embedded a full OCP microserver into it. Now that we have a switch that's more like a server, we can start developing software for it, just like we would develop any Facebook service. This switch software stack is called FBOSS. Control implementations. It also includes server management software that we use for all hundreds of thousands of servers in our fleet. Since last summer, we've deployed FBOSS at scale. The only top of rack switches. So we turned our attention to this, and we're excited to share today the Facebook 6-pack switch, our own 124 by 40 gig switch that is at the core of our fabric design. 6-pack uses wedge as the basic building block. As you can see, the 6-pack line cards look nearly identical to wedge. They have a high-speed ASIC on it, as well as a full OCP microserver on it. They can be managed separately, and 16 of the 40 gig ports face front, and 16 face the back plane. 2 of these line cards are then taken together, put side by side to create a fabric card. And the fabric card provides the non-blocking connectivity inside the 6-pack itself. If you look at 6-pack as a whole, we have 8 line cards with 128 ports facing out. There are 2 fabric cards that provide all the non-blocking bandwidth. And we now have the core of our fabric design. So there it is, 6-pack, the first open modular hardware switching platform. I'm Omar Baldonado, and I'm part of the Facebook network team.
Okay. Questions? Okay. So we saw about 6-pack, that is basically a new switch that was introduced by Facebook last year. Now let me go over the video, and I will stop at some points and discuss topics with you.
I'll go over our vision today for the Asst data center. When we started to think about this, we tried to redo everything with a focus on flexibility, scalability, and feature development speed. And so over the last year, we've announced different components of this new data center vision as they've gone into mass production and operational reality. First, we had to rethink the whole topology. We designed a new fabric.
Okay, here let's look at this picture for a moment. This is the topology of a data center. Okay, it's the networking topology of how the servers in a data center are interconnected. And it's also called fabric, like the fabric we discussed before on board. But this is something that is physical in space. Okay, so if we have a server in a data center, this is located in a pod. So it's dot here. It's basically a rack of switches. You know what is a rack, right? Okay, it's something that is 2 meters long, and basically you remember the visit we did last semester to the data center of the university, and we will see we might organize something this semester as well. Last semester we saw the computer, the network, but we didn't see the data center. We might do something similar for the data center. Okay, so it's basically dot here is a rack that has inside, you know, a few dozens, maybe more servers. Okay, and then the topology usually is organized in these 3 layers. We have a switch here that aggregates the systems on the rack. Then we have a second layer switch, level switch, that is more powerful than the switch here, that it aggregates multiple a pod. Okay, and then we have a top level switch that basically they can aggregate everything and they switch everything between each other. I'm not going to discuss in this course, it's beyond the scope of this lecture today, this topology, but in the second exercise we will do, you will have to build a topology like that, and there will be more material about this, the topology then. Okay. Okay, so this is the topology of a data center. At most, you know, Google, Microsoft, Facebook, they have these levels in their network topology.
Fabric topology that gave us the scalability and flexibility that our previous designs didn't have. Then we turned our attention to the switch hardware itself. There we started with the top-of-rack switch because it was the simplest place to insert new hardware and software.
The switch, the first networking component, is a switch that sits on the top of the rack. Okay, this is called top of the rack switch. Okay, so this is the top of the rack switch.
Into the network. When we design wedge, we wanted to be sure it would be more open and modular, and that it could be the basis for all future hardware and topology.
Okay, so I want to discuss this more, and I have a slide also further on. Can you read here what you see? Okay. So here you see the different parts of a switch of the hardware. You have the fans, you have the power supply, you have the ports. This is the 40G ports. Okay. Here we have something that is called the ASIC. I think it's this part over here. Okay, this ASIC is very important. It's the topic we will focus afterwards. It's the application-specific integrated circuit that basically it implements everything we have seen so far. Notice the input ports, the input processing, the switching fabric, the output processing, all this hardware is implemented inside here. And it's an integrated circuit, an application-specific integrated circuit. It's a little chip. Yes.
Why do we need the top of the rack switch? Why not get the middle of the rack, for example? Why do we examine the top?
It's just a name. They just call it top of the rack.
As I said, you get the top switch of the rack. There is a rack of switches and
No, it's a rack of servers. And all the servers connect to one switch.
Okay.
And usually the switch sits on top.
Okay.
Okay. So this is the ASIC and this is the CPU. Okay, this is the fast path and this is the slow path. That sits next to it. And on top we have the chassis. That's how it's called, the chassis, the box basically that closes it. We will see another diagram, or maybe let's see one right now before moving on. Okay, here we are. Okay, fantastic. So these are the slides which are online, and by the way they contain a lot of additional material you can look into. This is another switch. Okay, they all look more or less the same. We have the ports, the input ports, we have the ASIC that implements the diagram, the second diagram we saw. We have the CPU, and we have the memory of the CPU and the main memory. Okay? So this is the fast path. If something goes there, it's the slow path.
Yes, DRAM is upgradable in every switching or only in the. Because as you see, the DRAM.
I imagine yes.
It's a matter of implementation. There are switches that you can upgrade, there are switches that you can, like the laptop that you can, and laptop that you can.
And that it could be the basis for all future hardware and topologies. We also wanted to make the switch more like a server, so we actually embedded a full OCP microserver into it. Now that we have a switch that's more like a server, we could start developing software for it.
So this is important. What they call a switch that is like a server. They have their own SDN. They talk about SDN here, okay? And they mean that the switch is programmable. That's what they don't use OpenFlow. They have their own open API. OpenFlow is not, the only southbound API. But here they talk about SDN, like when they talk about having a server on the switch.
Now that we have a switch that's more like a server, we can start developing software, just like we would develop any Facebook service. This switch software stack is called FBOSS, and it includes our own forwarding and control implementations. It also includes server management software that we use for all hundreds of thousands of servers in our fleet. Since last summer, we've deployed the only missing piece was, what about all those non-top-of-rack switches? So we turned our attention to this, and we're excited to share today the Facebook 6-pack switch, our own 128-port by 40 gig switch that is at the core of our fabric design. 6-pack uses wedge as the basic building block. As you can see, 6-pack cards look nearly identical to wedge. They have a high-speed ASIC on it, as well as a full OCP microserver on it. They can be managed separately, and 16 of the 40 gig ports face front, and 16 face the back plane. 2 of these line cards are then taken together, put side by side to create a fabric card. And the fabric card provides the non-blocking connectivity inside the 6-pack itself. If you look at 6-pack as a whole, we have 8 line cards with 128 ports facing out. There are 2 fabric cards that provide all the non-blocking bandwidth. And with that, we now have the core of our fabric design. So there.
Okay, and now they talk here about not anymore the top of the rack switches, that is the ones that sit at the bottom level. They talk about the aggregation switches that sit further up, and these switches are bigger. Okay, these switches, they can cost millions of dollars if they would buy them from outside. Millions of dollars each. And for the data centers, they need the thousands of these switches. So it's a major cost for these companies. So this is the aggregation switch, and the speaker explains a bit some specifics of the design. That this is the internal fabric within the switch now, within the different line cards, and so on.
There it is, 6-pack, the first open modular hardware switching platform.
For this switch is open. I mean, everybody can implement.
Yes, it's like open source software. I think this is something that changes now. These years, the last couple of years, it's a major shift in the story of networking hardware design. Now, let me share something interesting here. So this is, as we said, the ASIC. It's the most important component of the switch. Actually, it implements everything we have seen so far. Okay. Who do you believe builds these ASICs? Who produces them? It's integrated circuit. Okay. Interestingly, there are companies like Broadcom is the most well-known ASIC developer for switching hardware, Marvell and others. Now, what is very interesting, most of the companies that produce networking gear, Cisco, Juniper, HP, Dell, Arista, they use the same ASIC, the same chipset. So this ASIC, it's the Trident 2 ASIC that is produced by Broadcom. In terms of the ASICs, the hardware vendors do not differ. They buy an integrated circuit from Broadcom, and they adapt this in the further design of their products. So the ASICs, a new generation of ASICs, comes out every approximately 2 years. Okay. It takes 18 to 24 months to design a new chipset. Usually
Broadcom takes 2 years to...
Yes.
So the winner is Broadcom from this technology.
It's a major player, yes. It's a major player. So, and usually every 2 years they come out with supporting more ports, having less latency and less power consumption. So this is what they try to do in the design of these ASICs. Then the vendors, Cisco buy them and buy the chipset, and then they customize it and adapt it in their final products. So one could use the same chipset to have 48 1 gigabit ports, while someone else could have 4 10 gigabit ports, but using the same chipset on the background, and so on. Now, and this is something that I really want you to keep from this lecture. And the reason we spend so much time today discussing the hardware is for the following key point. Traditional protocols like layer 2 protocols, layer 3 protocols, and their processing is built in on hardware. The hardware knows the protocols, knows the MAC protocol, knows the IP protocol, knows the traditional protocols that are used in computer networks. Okay. And this relates, of course, to software-defined networks, because software-defined networks try to make the network more evolvable and to detach it from the protocols the way we know them until now. It has a clever idea of the flow table, which we can program it the way we like it, and we can customize the processing of protocols and so on. But one of the major obstacles that to SDN is that hardware, the existing hardware in all most vendors, is aware of the traditional protocols and operates with the traditional workflow of protocols in mind. Okay. So one of the major topics of research nowadays and for the future of SDN is how do we design hardware for networking devices that is protocol agnostic, that does not know anything about protocol, doesn't know anything about MAC, IP, and so on. And this is a hot topic presently in the domain of SDN and in the industry. Okay, and this is also one of the things that is holding back SDN. Especially if you imagine that these chips take a new cycle, a new generation of chips comes out every 2 years. Okay, so it's holding back SDN. And now, and I want to add something here. Don't know where exactly is that slide. Maybe it's afterwards. Yeah, here. So the first generation of SDN switches, today most vendors produce open flow switches where we have a flow table. In the flow table, we know that we can put any rule we like. Okay. These rules were in SRAM. These rules were either on software in the slow path. The flow table was implemented in SRAM, or when it was put on hardware, the flow table. Can you imagine which memory was used here to implement the flow table? Which of the three memories? Yes?
Probably level 3 CAM.
No. It was used the TCAM, because here we can have wildcards, and in flow table we need wildcards. So basically, this memory that was designed for firewalls, for access control lists, was the only hardware memory that was used in the fast path that is used by still to implement the flow table. And here we only had 4,000 entries. We could have only a very small table. Okay. So this is one of the main challenges in SDN-related activities, and it's a hot topic nowadays.
So what would you say an ASIC is? Okay, I got it. It is a chip, and it exists inside the switch. But what would we say it's the job it does?
Do you remember the second diagram we designed?
The fast path.
No, the second. That was the first. The second diagram.
Okay.
Input processing, fabric, output processing.
Where is the ASIC inside the diagram?
No, all the diagram is inside the ASIC. Okay, so one last thing before we close today. You can see the slides. So read the slides here. So we talked about OpenFlow in the last lecture, okay? So the OpenFlow implementation on a switch sits on the software, on the CPU side, okay? But OpenFlow is not the only protocol that is used to control a switch. OpenFlow has a sister or a brother that is called OFconfig. Okay, and OFconfig is used to do functions like initializing the switch, saying to the OpenFlow agent where is the controller, taking ports up and down, configuring ports, enabling disable. It's like you can think it like the BIOS, that manages the hardware a bit of the switch. It can also be used to virtualize a physical switch, and we implement two software switches. Okay, so in reality we have two control protocols. The one is OFconfig and the other is OpenFlow in the OpenFlow standardization, in the OpenFlow standard. Okay, the slides this is fairly simple, you can read it in the slides. Okay, so this is all for today. So thank you, and see you next Tuesday.